we have responsibility to model 87,000 square miles in northern Mexico. So we will coordinate with the Mexican government on the interior points, but the second it hits the boundary, it's us. We have to deal with literal desert, El Paso, New Mexico, to literal swamps in Lake Charles and far southeast Texas. Snowpack and snow melt in the west, very super critical, and then their monsoonal activity. As we move, into Texas, especially in the hill country area where you have steep, rocky slopes, and the chance to get some heavy rain, you can get really rapid river rises, flash flooding, and it's the term coined flash flood alley. If everyone thinks of a tornado alley being in the plains, well, you can say the hill country's flash flood alley. Anything along the coast, you've got a tropical influence. It slows down because the topography flattens out, so to speak. And then anything up in North Texas, there's only one natural lake in the state of Texas, and it's not in my area. Every other lake, who designed it, what is it designed for, and let's coordinate when it comes time to make releases. So, 400,000 square miles total, and it's a challenge every day, and I look forward to that challenge. I always chime in that Texas has a lot of billion-dollar disasters, and I'm going to follow up with some more information later. Yes, we have droughts. Yes, we have hailstorms, but flooding really kicks in there. We've had multiple floods. I tell a lot of people, if it wasn't for Harvey, people would be talking about Imelda being the flood of their lifetime. And they happen just a year or two apart. Our floods, the 2002 flood event, the 2007 flood event, the 2015 and the Blanco. We have billion-dollar events, and they're not always tied to a tropical storm. So I tell everyone, be prepared. Yes, tropics are active. Yes, we can get large flood events during tropical season, but we can get large flood events also outside of that as well. And if you're going to focus on the tropics, don't just focus on the Atlantic. Focus on the Pacific too, because Pacific storms can also feed into this billion-dollar disaster. You see, Texas has had $124 billion disasters since 1980. It's easily the most of every state, but it ties kind of into my future points. We have a larger footprint, and if we are more vulnerable, then we're going to have the opportunities for Mother Nature to cause more damage. And the best way to explain it, why do we have such flood damages? It's because humans have decided that Texas is awesome and we want to live here. The risk is the threat times the vulnerability. The rainfall threat has always been there. I'm not going to get off into climate change and or global warming or anything like that. I'm going to say that Mother Nature has always dropped heavy rain events. What has changed is the vulnerability and the footprint, because a rain event that hits the north side of Houston in 1980 and a rain event that hits the north side of Houston in 2021 are going to have different impacts because the vulnerability changes. It's the same with the hill country. It's the same for anywhere that's a large urban area. Okay, so as we increase our vulnerability, as we increase our footprint, where we live in places we weren't living before, we change the hydrology and we increase the risk that flood event or that rain event is going to cause a significantly greater flood event. Okay, so here's an example that I use here in the Dallas-Fort Worth area where we're located. Look at the buildup around the Dallas-Fort Worth area from 1979 to 2003, but more importantly, there are lakes added to this equation. Okay, so these lakes can impound. It goes back to my other point of you got to know your reservoir operators and what those lakes are designed to do, and then what they're going to do when they start getting full. But as we increase the urban area, you take land that could absorb water and you put runoff, you put a roof, you put a parking lot, you put some form of concrete, it's going to be 100% runoff and a lot faster. So you've changed how that area responds, and you've got to change your forecasting paradigm as well. And just to give you an idea now, I mean, the Dallas-Fort Worth area, the fourth largest metro area, it expands, multiple counties up here, probably 900, each county is what, 900 square miles. And we've got 7 or 8 counties that this is a huge urban footprint that you now have to work to anticipate the rain events, to anticipate the runoff, the increased speed. It's going to get there faster, and then sending all that downstream. And Houston does not escape from it either. If you look at the Houston area, I remember growing up, you used to drive a couple of miles through the forest to get from the Woodlands to Spring. You used to drive a couple of miles to go from the Woodlands up to Conroe. It is now packed all developed, suburbs and strip malls and that all the way up to Huntsville. And the same way when you're going south of town, if you're going towards Galveston, I mean, it used to be there were pockets of area that you waited in anticipation to go see the beach. It is now built the whole way. And as the footprint increases, then your vulnerability increases and the risk of a heavy rain event. And so what I tell everyone is that Harvey was not an unprecedented storm. It had unprecedented impacts, but Harvey was a major hurricane. It made landfall along the northwest coast of the Gulf of Mexico. Its remnants just sat around and drifted around 30 degrees north latitude, and it produced rain and flooding that area had never seen. It is still being referenced. We're still doing studies on it. But the storm I'm explaining now is actually Hurricane Alex from 2010. The difference is it hit in northern Mexico and flooded the tributaries and flooded the Rio Grande down through the waterways that the International Boundary Water Commission maintains. The point is that Harvey is not a once-in-a-lifetime storm. I have worked a Harvey-like event already in my career. I worked one in 2002, and I'm telling everyone, be prepared, okay? Mother Nature finds a way to throw these things at you, and what is your vulnerability? What is your risk? And the best way to do that is give you the information ahead of time. If we can get you a forecast so that you can move assets and be prepared, that helps out as much as we can. So with that, we talk about the water cycle. The National Weather Service deals with almost everything except the groundwater component. Our weather models, they take into account, the moisture that flows from the Gulf of Mexico, from the Pacific, or from the Atlantic. We try to anticipate topography and lift and all the things that go into the atmosphere to produce rain. And then once it hits the ground, the river forecast centers take over with rainfall, rain rates, soil conditions, runoff parameters, timing parameters, and routing parameters so that we can get it, back to the ocean and start it all over again. A lot of people say, man, that's a lot going on there. I said, yeah, but my friend Phil Baker, his kindergartner, wrote this up and said, hey, Mr. Waller, does this look great? And I said, you've done an outstanding job. If a kindergartner can grasp the concept, then we should be able to communicate these matters to individuals so that they understand the forecast and that they can make actions based on it. The forecast is simple. We take the rain that has fallen. We take a forecast rainfall. We can go 24 hours routinely in our river forecast. We can go 3 days, we can go 5 days. I'm telling you right now, the accuracy in the weather being off just 30 miles can mean the difference of a different county, a different complete river system. And our accuracy at 24 hours starts to decrease from that point on. So we use 24 hours, but we will run a series of future rainfall events so that we're prepared just in case. You put the rain on the ground, you put the forecast rainfall, you put it in your soil moisture model. Are the soils saturated? Will it run off? Will the soils infiltrate and percolate down? You then combine in those lake releases. Remember, every lake in the state of Texas but one was designed by a human for a reason. So please tell me what you're going to do with the operations, and we develop trust over time so that these river forecasts reflect the latest and greatest information from our reservoir operators. Once we issue it out, it's a height forecast, but the National Weather Service would want you to know that once we issue the forecast and it gets above a certain criteria, we will issue flood warnings so that the media can pick up on it and so that you understand flood warning. In the Weather Service terminology, warning means life-threatening and it's imminent or occurring. Another thing, though, is that telling me a point on a river map doesn't help me. I need to know how big the water is going to be. I need to know the depth of the water. I need to know a map of areas that are going to be impacted. So the West Gulf River Forecast Center has been leading the nation in working with our National Water Center on getting what's called R&R. They're going to replace the national water model with our official forecast because it's the best forecast. And we're going to use the water model to send that downstream and create flood inundation maps. There's a lot that goes into these, and we use flood inundation maps to try to identify vulnerable areas. A forecast inundation map is going to have more uncertainty, but an observed inundation map is going to help first responders. So what I tell everyone is if you don't have a flood inundation map, or you don't know someone that does, find someone, get an expert in there to be able to help us, diagnose all this. I know that Harris County has, flood inundation maps as well, but this seems to be the way of the future. It's not a river forecast point. It's a map that shows the areas that will be impacted. I also say check out Inform. It is a multi-government, multi-agency operation with the USGS, FEMA, the Weather Service, and the Corps of Engineers so that we can put All of these maps that are available, as they get approved, we can put them on a national site, and you can go and look at them anyway without having to look at the water center map or go to another web page. We also try to do advanced precipitation analysis. After Hurricane Harvey, we did a long-term analysis to determine, with all this new data, because the last analysis was done in the 70s, by NOAA, and we said, is there new information? Can we identify the chances of heavy rain events? So the new NOAA Atlas 14 data was released a couple of years ago. If you're doing studies on it, please download that data to determine your 100-year, your 500-year, your 50-year rainfall frequencies for various areas. What we can say is with the new data, we know that the 100-year rain event in the Southeast Texas area, we had to beef it up. And we know that the 100-year rain event along the Rio Grande from Del Rio down, we had to beef it up as well. So we know that with the new data that we had to adjust our frequencies on these rain events. The meteorology, that's where my degree is, even though I'm a hydrologist by title. The meteorology is, let's use a multi-sensor precipitation estimation program. It's a lot of words, but we break the entire area into a 4-kilometer grid, and we try to run it every hour. That time step is pretty good for rivers on my scale, but Justin's going to come through and talk about the time scales that they use. A 4-kilometer grid on the hour, give me data. Give me a radar, give me a satellite, give me rain gauges. You say, well, radars are really good. Why don't you use radars more often? They're great. They give you a spatial representation, but as the radar beam gets further away from the radar itself, it's going up at a 0.5 degree elevation. So there are times that it starts getting 8,000, 10,000 feet above the ground, and there can be a lot of meteorology underneath it that we're missing out on. So I say, give me a radar and then give me a bunch of rain gauges that are accurate to calibrate it, and that way I can get the best product possible. In the case, of Texas, you look at where the National Weather Service radars are located. I've got the Trinity River Basin there. You can see the locations of the Dallas-Fort Worth radar, the one that's around Temple, Killeen, the one that's around Austin, San Antonio, the one in Houston, the one in Shreveport. There are sections of Texas where the lowest radar beam is over 10,000 feet in the air. So I really need rain gauges to fill in that gap. So everywhere that's in white is where the radar beam is over 10,000 feet. So I need some gauges to fill it in. If you combine the best of the radar, the best of the gauge, and then fill in with satellite where you can, and the new satellites are doing a really good job, your end result is going to be a lot better. Okay, so give me some rain gauges, give me some radars, and give me some satellite. Our rainfall forecast have gotten a lot better in my career. In the last 20 years, I believe our 7-day forecast is now as accurate as our 3-day forecast was when I first started. And I really am hyped up with some of our high resolution models. But what we've learned is we grab the best of all of the weather models we have available, and we use some human influence and some tweaking to really improve on the rainfall forecast. We verify that the same way we fill in the gaps with rain gauges. You can see this is just 1 hour where I pull the rain gauges from across the river systems, and you see, the Dallas-Fort Worth area, Dallas Alert, Tarrant Regional Water District. You can see the Harris County Gauge Network down in the San Jacinto River. You can see the Colorado and their LCRA network. You can see pockets of areas where we have good gauge coverage and some areas where we have less than good gauge coverage. So we're working with the Texas Mesonet. Let's identify and fill in these gaps so that way we can have a good rain gauge network. It helps with the rainfall forecast verification, and it helps in the real-time precipitation estimates. So here's an idea of the rainfall forecast. We use our national guidance from our national center, but again, we break this down into smaller time skips, and we use our local expertise to put in the river forecast model. And this is the point where I say our forecast is based on a forecast. If you're off just a little bit on these large scale events, it can affect completely different river systems. So we're always updating them every 6 hours. We're updating this rainfall forecast, and we run it out 5 to 7 days, but our main river forecast goes out only 24 hours of future rainfall, because after that, the false alarms start really riding over and our accuracy goes down. We use a soil moisture counting model. This is kind of busy, but just think of it as buckets and different layers of the atmosphere of the soil. You use upper zones, lower zones, what's complete surface runoff. You can add in a vegetation component, so it takes it out in the summer, but does not take out water in the winter. There's percolation. There's all sorts of parameters that we can use to try to estimate once the rainfall comes down, how much of that's going to fill into and saturate the soil and how much of that's going to run off. We know that there's timing component. So we've got to do the timing of the local rainfall and the timing of any rain and water that's coming upstream. So we have routing parameters, we have attenuation parameters, and this is all done routinely about every 3 or 4 years. We go back and redo it all to determine what has changed in the watershed, because if you build a subdivision, the timing is going to change. I told you, you're going to have more runoff faster. So we do our timing calibrations periodically, and we try to take into account the local rainfall and the routed water coming down. When we put it all together, you can have a bunch of squiggly lines on the map, but the hydrologist knows when they look at a series of observations that comes from either the USGS or Harris County or whatever, we know what components are supposed to be local, what are components supposed to be routed, the soil moisture, all that. We can adjust what we need to adjust. Okay, so at this point, that's where the skill of the hydrologist. You can push a button and get a pretty cruddy forecast out in just a matter of learning in months, but our experience, 5 years, 10 years experience of the hydrologist, and they understand the model and they understand how the basin reacts. We can then modify any of the parameters that I've talked about: past rainfall, future rainfall, soil moisture, upper zones, lower zones, routing. The hydrologist has the ability to modify all of those to put out the best forecast possible. But that's for the large scale river systems, okay? If you get to a smaller scale that's more urban and faster, you're going to have to kind of change your process. So with that, I'd like to kick it over to Justin and have him explain how Harris County tackles it on a smaller scale.
Thanks, Greg. Let's get this started. All right, so we're going to transition a little bit to get a little bit more in the details and look at some comparisons about how we compare our data and really how well we're doing at communicating this information. To preface this presentation, our history in forecasting is fairly brief, right? We've only been doing this for several years from an operational aspect, and so we don't have a lot of that. We have a lot of that operational knowledge from the monitoring and from experiencing events, but we don't have that knowledge from a forecasting standpoint. So there's a lot of ground that needs to be made up on our part. And so we've done, early investigations into forecasting where you apply paper approach, looking at, FEMA maps, looking at rating curves, looking at historical events, or, early model simulations and studies that have been conducted in the past to model small areas. But this effort for us really didn't start until we jumped into 2016, 2017, early in my career in Houston, where we started with the software evaluation to really identify how are we going to approach forecasting in Harris County. And that, of course, leads into this natural process of doing a pilot, doing your development, implementing it, and getting it integrated into a fully operational system, which is where we are now and have been for a little over a year. And we continue to improve our systems, and you can see here kind of like the progression of how we had tackled Harris County. We approached it with a single watershed, then we added 2 more, then we added 5 more, and it ends up adding up to the 22 watersheds that make up and contribute to Harris County, with some exclusions, right? So we don't incorporate portions upstream of Lake Conroe, which is located up here. And we don't do reservoir forecasting, which is something that's different, or we don't have the operations tied into our models, which is something that's different from the river forecast centers. So I called it the water cycle here. I'm gonna hide all this here in case it's blocking the screen. So, I called it the forecast cycle. Water cycle's been covered. I hope we all understand that. The forecast cycle for us starts with data collection. Goes to you're processing that data, get into a format that your model can understand it. You then ingest it into a model, run the model, get your results, and process them into a format that you can then digest them, right? So the model has to be able to understand the data. You have to be able to understand the data. You got to review those results and communicate. And communication is both internal, external, with partners, with the public, and it exists on multiple levels. It's both on your local level, your state level, and possibly your federal level. It's got a federal partner involved, with the National Weather Service being our biggest federal partner that we collaborate with during events, and on a maybe bi-weekly basis. I think I'm in touch with 1 or 2 different people from either the River Forecast Center or from our local WFO, talking about things that we're working on, changes that we're trying to make. How do you do this? How do we do that? And so it's this kind of constant process. So our system give you a brief overview, we use an application called HCFCD. This was developed by HEC and is used by the Corps, also known as SWIMS, or the Corps Water Management System, to do their reservoir operations forecasting, right? RTS is the desktop application. It couples, essentially, the HEC applications that you need to do forecast modeling. So your HMS models, your HCRAS models, there's some inundation applications and impacts. There's some kind of what if scenarios and development kind of future planning applications, one which is called WAT, and some rainfall modification, meteorology-based applications that can all be coupled into HEC-RTS. For our purposes, we use HEC-HMS only, and we're using version 4.6.1, which is the version that comes with the latest version of RTS. And we use rating curves to get our stage. So the image here shows on the right, shows the locations where we are producing forecasts, so the 170 plus locations, both in and out of Harris County. We've got a model domain that's about 4,000 square miles, not quite as impressive as the River Forecast Center's domain, but it's still a large domain for us. And it has, to give you kind of a measure of density, we have 1,100 plus subbasins in our model, which in my experience is the largest HMS model that I've been a part of building. And it's raised certain challenges that we've had to address throughout the process. But it's required to have that level of density and detail because of the urbanization level in Harris County. A little bit about the modeling approach. This ties into what Greg was pointing out there. Hydrology, from a hydrology standpoint, HMS is our driver. The methods we're using, green amped for our infiltration and runoff model, Clarkina hydrograph for our transformation to get that into a overland flow, a discharge in the stream. And then our routing model uses Muskingum and modified pulse. These are fairly standard methods inside of HMS. I think the image here on the right shows that pretty decently. Again, aspect that we're missing is base flow. For event-based modeling, the base flow doesn't play a huge role, especially with the soil types that we have in Harris County and the surrounding areas or Cindy Center watershed. It's not a big player. And so that's something that we kind of disregard as a part of our modeling and assume it to be negligible. From a hydraulic standpoint, we do not have a coupled hydraulic model. Therefore, we're using a ratings-based approach. And these rating curves are a part of our calibration process. They utilize discharge measurements that we take at our FWS or HCFCD maintained gauge locations. If it's a USGS site, we're going to utilize their observation points, or field measurements, or rating curve that they've defined there. And then we'll supplement that information with some model rating curves where we may not have, say, a measurement. So if you have a site that's fairly new, maybe you've only collected 1 or 2 measurements during an event, there's going to be a lot of missing pieces there, so a model can help kind of fill that gap. Some of the limitations of our model, this is just to name a few. We do not have a soil moisture accounting process that's incorporated in with the green amped. This is something that's been somewhat addressed, I believe, as a part of the layered green amp approach that's built in the newer versions of HMS. So it's certainly available, but it is a limitation of our current model. And being a HMS only and no dynamic modeling integrated with the hydraulic model, like HEC-RAS and STEADY, like a 1D model or even a 2D model, we don't have accounting for backwater or tidal influence. So to play on a scenario, if you had an event that had some elevated tides or had surge, that is something that would not be considered as a part of our forecast by default, and we'd have to make the observation and manual adjustments to be able to account for that. So I mentioned that our model is complex or has a high level of density for our region. So initially we tried to run this as a single HMS model. So 1,167 subbasins plus a routing reach, not for every one, but we could assume that there's one routing reach for every 2 basins, and then a lot of junctions, a lot of rain curves, a lot of forecast scenarios, different ensembles, and that adds up to a lot of time, a lot of memory usage. And time is of the essence when generating forecasts. So we had to come up with a solution for reducing that runtime and in some cases being able to complete a run at all. And so we split the model up into two regions, a northern and a southern region. It just happens to be that the southern region is our more urbanized and the northern region is our more rural watersheds. So it actually pairs pretty well for what watersheds are integrated with each other. There are some shortcomings. For example, the region between over in Addicks and Cypress, there's an overflow region here that is unaccounted for and requires diversion of flow from one to the other. And there are processes that can pick that up so that that flow gets diverted there. That's more of an edge case. It's not something that happens on your regular event. And so it's something that we don't have to worry about all the time, but obviously something to note. And then when it comes to our reservoirs, we would take any forecast that would come available from the core and ingest that as, say, an observed flow or some type of source flow into our models to help with modeling on Buffalo. And if you're curious what an HMS model looks like of that density, this is what it looks like, split up into its two parts. So one of the other things we're doing to address this issue is, runtime is obviously a concern. Simplification of model regions. So take the San Jacinto, for example. This consists of something like 250 subbasins, which means you have 250 basin elements, a lot of reaches, a lot of junctions. So we've been able to simplify this down to something closer to 80, which I think is appropriate for the gauge resolution, the number of forecast points that we have out there, the supporting observation data. And so that has resulted in a reduced runtime. It still provides us with a reliable forecast, but these are opportunities where you can kind of reduce your resolution without the consequence of losing your accuracy. So what are some of the data sources that we use? Obviously, we are ingesting rainfall from our gauge network. We bring in information from the National Weather Service, some MRMS-based gridded data that comes in every 2 minutes. We have a third-party product from View and Associates that provides us with 5-minute gauge-adjusted radar rainfall that utilizes our gauges. We also have forecast rainfall products. We're pulling in the HER, HREF. We have the XMRG, which is the NPE product that, and the QPF product that Greg had mentioned previously. And we have the option to do kind of a what-if scenario or manual forecast based on that. So we readily produce ensembles for the first 4. 5 and 6 can be ran optionally. 5 only gets updated every 6 hours, so we don't need to make that run every time. Same, I believe, is the case for the QPF for the XMRG. The NP would come in every hour, slightly delayed, I believe. But that's also something that we can run as an optional, and it is certainly something that can be included. Each of these come in a different format, right? So some of these are coming in as XML files. Some of them come in the standard National Weather Service GRIB format. So there's a lot of processing that goes into getting these into a format that we can digest, and also the transformation process. We have point data, we have gridded data. All this has to be translated into the basin format because our models are nodal parameter models, not distributed models like some of the options that are out there. And so there's that transformation process that exists. We're also ingesting in observation data from some of our partners, USGS, SGRA, and others. And then, of course, we're bringing in, as a part of our collaboration with the National Weather Service, the forecasts that are produced by the West Gulf River Forecast Center. So how do you connect all these pieces? So over here on the left, we have the raw data coming in from all of our sources. That gets pulled in by a virtual machine that's doing our data collection, our post-processing. And that's where the process of getting it all into a common format, doing the transformation, changing the time steps from hourly to 15-minute or from 2-minute to 15-minute, all of that's occurring on that machine. That happens every 15 minutes. It goes and checks for new data. The process of collecting all of that data from all the sources that we get it from and getting it into DSS, which is the format that is required for HEC RTS, takes just under 5 minutes. And there's opportunities to obviously improve that, but the more things you add, more sources you add, the longer it takes to process. And so you have to be smart in how you approach download that data. It's not practical to go download the past 2 days worth of data from an MRMS server or from an LDM if you only need to get the last 2 hours. So you need to be smart about how you approach that. So all the data gets downloaded and processed, gets prepared, put into a DSS, and then the model simulation happens on a second machine. This is where we have 2 instances of HEC-RTS running side by side, one for the north region, one for the south region. It goes, pulls in the individual information, generates a forecast for the scenarios that I talked about previously, spits them out into results, DSS or a forecast DSS, where we have all the observation data that went into it, all the results data that came out of it is stored within that file, gets picked back up by the first machine, processed, and that's where, once we've got past this post-processing step, we're generating graphs, tables, XML files, pushing it to a SQL database. This is where our communication happens. So I've bolded out a couple things here. We have an LDM server that we operate, excuse me, out of Harris County. And that's how we push our data, our forecast results to the River Forecast Center. That's how we pull their forecast. That's how we get the QPE and the QPF data from them. There's also some other things that we get from them as well through there. But it's basically a way of transmitting data. And it's worked extremely well, I think, considering it's only been stood up for just over a year, maybe a year and a half. And so that process has worked well. We also generate forecast plots that they can look at that we'll share via OneDrive or Google Drive, whatever means. And that's really a secondary level of sharing. They can look at our forecasts in their system at their forecast points, but what if they wanted to see something that's happening on a smaller stream where they don't have a point? That's where our forecast plots come in. We also are pushing our results to a database that would be coupled with a operational interface that we're in the process of developing and should be wrapping up here within the next month. This is going to basically be our operational interface for looking at forecasts and communicating that. The goal is to get that access to our partners that we've worked with closely, specifically the National Weather Service, so that they can see our forecast results inside of our system without necessarily having to share a forecast through some type of file sharing application. So this will be extremely helpful for us because it broadens the number of internal users that have visibility on the forecast. It's not limited to a couple of forecasters and the staff that do our flood operations, Jeff and Jeremy, as a part of our hydrologic operations division. It's getting people who need the information, access to the information without having to go through a model or go to a location on the server. It's a website, it's easy to use, it gives you prompts. And so that's going to be extremely beneficial for us from an internal and external communication standpoint. And this process happens every hour. Our models take roughly, with recent updates that we've made, they take roughly 10 to 20 minutes, depending on the size of the event. The larger the event, the more rain, the longer it takes to process the data. That happens at the modeling level, that happens on the pre-processing level, the post-processing level. More rain means more time. And so we're able to up this information every hour. Ideally, you can do it more frequently, but we have to allow time for digesting the information. It's kind of hard to interpret a forecast that is constantly changing. And so one key part of operating a forecast system, or really anything, is understanding your limitations. And so we recognize that our models are not going to be perfect at producing a forecast for a stream that responds in 15 minutes. If it takes our model 15 minutes to run, and that run doesn't occur until 30 minutes after the rainfall hit the ground, or even if it occurs only 10 minutes after the rainfall hit the ground, we're already 25 minutes behind, which means that the stream has potentially peaked 10 minutes ago. So there are practical limitations to forecasting that we have to take into consideration. And there are ways around that. For example, you could incorporate short range QPF, but QPF, as Greg noted, has its challenges, specifically or especially in Harris County, where we have small watersheds that if spatially your forecast rainfall is off, or if from volume standpoint or timing standpoint, the volume is off or the timing is off, then you not doing yourself a lot of good if the rainfall is in the wrong place. And so we find that, you know, QPF, although helpful, has its limitations in some of our areas. I had mentioned the backwater and tidal influence. You know, these are addressed with dynamic modeling, unsteady models that can help address that issue, or other lookup methods and interpolation methods. We also have forecasts only at our gauge locations, and this goes to Greg's comment about a map, right, or a profile, which allows you to see what is my interpretation of the forecasts in between the gauges. Because although we have a lot of gauges in Harris County and surrounding Harris County, we don't have one at every bridge. And so it's helpful, or in every neighborhood. And so it's helpful from a forecasting standpoint to know what that looks like spatially. And that's something that, you know, is certainly to come in the future. We also don't do urban overland flow or street flooding modeling. That's really difficult to do on the time frame that's practical for forecasting. And so, you know, we can leave that out. And then, of course, you know, the event is going to dictate the outcome of the flood. And the model is not going to be able to do that 100%, 90%, 80%, 70% of its actual accuracy every single time. It really depends on the event. So let's look at some examples. These are some of the plots that we look at right now without the dashboard. These are some of the plots that we generate during an event. And what are we seeing here? We have a black line on the center plot here horizontally that represents the blue line represents real time. So that's the water level recorded by the gauge. Then we have a black, red, and yellow line. Each of those represent our forecast ensembles that are generated from, in this case, real-time rainfall only, no forecast rainfall. And so we can see the progression of the flood as we go through, starting early on on the 21st at 1900 local, and then on the 22nd at 0700 local, and then on the 23rd at 1930 local. And so you can see how the forecast progresses and how well it tracks. Typically, we have a lead time, depending on the size of the location, of the size of the stream at that forecast point, a lead time of about 2 to 4 hours. Larger streams, we have a longer lead time. Smaller streams, you might only have 15 minutes. So it really depends on the location. But in this location in particular, we do have about 2-hour lead time. Another example of some of the products that we produce, this is a forecast progression plot. And so this shows at Gassner Road for beta, the individual forecasts produced throughout that event. That's the red lines. That's each forecast we generated. The black line represents the ultimate forecasts. So if you took the maximum values of each one of these forecasts, that's what the black line represents. And then the blue circles represent the observation. So what actually happened there. And so we have pretty good agreement at Gassner Road for this particular event. Really throughout the event, there are some gaps in the second peaks and some of the recession is off, but this is a fairly valuable, very valuable forecast, and at least predicting, okay, are we going to get within the vicinity of our top of bank, which is this red line at the top. And that's kind of transitions us into our partner communication. When I started with the district back in January 3 years ago, we started this communication specifically around forecasting, because one of the biggest challenges of emergency management and communicating risk is consistency of messaging. And we wanted to make sure that if we're generating a forecast, if the National Weather Service is generating a forecast, which they are, and they were producing one prior, that we're not contradicting the forecast that's being put out. A lot of our forecast information is used internally and internally with our external partners, right? So it's official use only. We collaborate on our forecasts, as I mentioned previously. We're sharing it, we're talking about it, we're comparing them, and that might be via text, that might be via NWS chat, it might be via automated file share. And so we've established expectations for how we're going to communicate on these products, basically set the expectation that this is where we're going to meet. It's going to be in NWS chat. We're going to talk about it. if something looks of concern, if we have a question, we raise that question, we talk about it, and we get a warning out, or whatever has to go out gets addressed quickly, so that we can move on to potentially the next problem, right? So we're doing these coordination meetings. We hold them roughly semi-annually, maybe twice a year, and we have our constant communication that's ongoing. And I think that that's been extremely helpful for us in, one, identifying risk and raising warnings in areas where we may not been able to produce warnings prior. We certainly could have produced them, but we have a little bit more information about when is a good time to raise those warnings. And two, it allows us to learn from each other. There are certain areas where we might be able to provide some insight as to the risk from a flood, simply because we have a model that touches in that location, whereas the National Weather Service, the River Forecast Center, has years of experience in forecasting that we can leverage to try to improve ours. And so we can look at some of the comparisons of how we did. Let's just look at Nicholas from this year, because it has been a relatively nice and quiet year. And so what do we have here? We have just the operational plots that we generate. There's multiple ensembles on here from our forecast. That's the black, yellow, the darker red, kind of burgundy color, and that bright pink color. That's the bright pink color is our HCFC gauge forecasts with the HER 12 hours of the HER or 24 hours of the HER forecast added on to it at whenever real time was. These were produced after the fact, so we're looking at kind of a hindcast of what happened with all the data. But what we can see is comparing any of those lines to the light pink line or purpley line, I think it's called light violet, they compare pretty well. And this is on Clear Creek on the southern side of Harris County. And you can see how well they compare. There's obvious differences, right? The River Forecast Center tracks extremely well on the rising limb. We both happen to capture the timing, and the peaks are really well represented with respect to one another, both over predictions of reality, but helpful still that we have kind of concurrence on what our timing would be. And then there's differences in the recession, but we have general agreement as to what the peak timing and elevation would be. And so that's something that we could say, okay, we at least feel comfortable for this. And then as the forecast progresses, you're going to be adjusting your perception of the forecast and modifying your forecast. Another example would be on Brays Bayou, South Main Street, about mid-watershed. You can see, again, comparison. The blue line is the observation. All the colors represent our forecast. And then the light pink is the forecast from the River Forecast Center. This is a well within bank, kind of event occurrence. And the forecast, it tracks extremely well. We tend to do really well in urban streams because of the geometric section, and we have a pretty good grasp of how engineered systems work. They're designed from models, and so I would hope that we could model them pretty well. And then the River Forecast Center, we're tracking extremely well. They come in a little bit low at this location, but there's examples of where we are blown off from a forecast and they're right on point. And so this happens, it all is a matter of scale. At this level, accuracy is not as critical as being up higher in the stream. And so this is still pleasing to see because you see it from a timing standpoint, we're in agreement. Within peak, we're within a couple feet of each other. And if this were a greater event, you certainly would see agreement between the two. And then one more, White Oak. Nicholas was a relatively small event for us for anything north of the south side of Harris County and some of our coastal areas that would have been influenced by some elevated tides and some surge. But again, good timing agreement. In fact, you see that the River Forecast Center tracked extremely well early on, both in the height and the timing. We're a little high on the timing, or on the peak initially. Timing is still reasonable though. And then we have good agreement on the second peak as well. And so this is just one set of examples of some of the comparisons between our two systems. And it's just proof that you can have a system two systems which utilize very different methods. One is a distributed model, one is a nodal model. They both use different hydrology. They both have different subbasin sizes. They both use different routing. Hydraulically, the rating curves are derived differently. One is based on USGS with the River Forecast Center, whereas we take a little bit of liberties and making adjustments to ours because we have supplemental information that we can incorporate. And so you can see how these two methods really do blend well together and serve the higher purpose of providing a better message. And so with that, that covers everything I have for today. Of course, if you have any questions, feel free to reach out to myself, reach out to Jeff Linder. I'll be happy to talk to you about any questions you might have, and I'll pass it back to Greg and Matt.
Thanks, Justin, and thank you as well, Greg. So we have a two-part question here, and I believe this is directed to Justin from Ranjan Matia. He asked, how do you handle storm drain discharges?
So storm drain discharges?
Correct.
So a lot of any urban drainage or overland flow, all that is captured in our parameterization of the model. So we don't model specifically an outfall from a neighborhood or from a roadway. What we're modeling is the area as a whole. And so although our areas are smaller, to give you an example, our catchments or our subbasins are about maybe 2 to 5 square miles, which is really small. They don't go quite down to the level of detail of the individual neighborhood, and so it's just captured as a part of our parameterization.
Okay. And the second question he asked, are you able to generalize your results? For example, better understanding of lag times between rainfall and discharge peaks, and what's that range?
They can certainly be generalized by reach or tributary. I have found that there are differences, obviously, between an urban watershed and a rural watershed, where you have maybe 24 hours on a rural watershed of response time and an extended recession. On an urban stream, you're going to have an extremely short response time and a quick recession, depending on the scale of the event. And so, yes, we have been able to, and it does differ from, reach to reach.
Yeah, sure. So Jeff Brizendine says, great presentation, guys. Great info and nice work.
Thank you.
Question from Shiva Sandrana. They say, how is soil moisture getting accounted for in real time? And why did you choose green and AMP as the infiltration model over other infiltration models?
So for Greg and the River Forecast Center, they're using a soil moisture accounting model. So they are modeling the actual soil moisture percentages during event. They also use something just called kind of continuous forecasting, where they take the conditions of the previous forecast at a specific time, or you could call them state variables, and those get used to initialize the model. We started using that similar concept in our modeling for continuous forecasting, where we'll run a forecast and then we'll take the state of the runoff, state of the infiltration, the soil moisture content, all that stuff, and use that to initialize and warm up our next forecast run, so that we are able to basically continue a forecast from the previous one. And that helps with runtime. It helps with accuracy of recession for longer events. For actual accounting, we don't obviously have that because green AMP is limited. We chose green AMP because that's one of the standard methods that's used in Harris County. It's a part of our drainage criteria. It's very common and well known amongst engineering firms. And so if you're working with engineering firms in Harris County, as this was not an effort completed by just individuals in Harris County, it's been a long-going effort, comprehensive effort with multiple companies to make this process work. that's one reason why you choose to go with Green Amp. Like I said, there are opportunities to improve on that. The new Green Amp method does allow for some soil moisture accounting, I believe, with the layered Green Amp. And so it's certainly something to consider moving forward.
Okay. Question from Jason Pinza for Justin. They say, how do you account for snowmelt in flooding considering its delayed nature?
Fortunately, we don't have to deal with snowmelt often or ever. I think that Greg would be able to better answer that with how they handle that.
Yeah, if I had to worry about snowmelt in the Houston area, I'd quit and move somewhere else. We have, from time to time, we do have snow events that come through. What we do, we have a snow melt water supply model for the Rio Grande that starts in southern Colorado, and we send it all the way through Albuquerque, and then we also have one that runs on the Pecos. So we actually take that into account. If it falls in any other river basin, what we do is we delay the rainfall so that the liquid equivalent is still going to be used in our soil moisture accounting model, but we delay it until the day of thaw. So if it rains on it, or if it snows on a Tuesday and stays that way, the precip products will still show it, but our soil moisture model will manually take it out. And then when we notice that it'll start thawing, then we add that volume of water in and then let the soil moisture accounting model do its calculations from there. So I always joke that I call it delayed rainfall if it's in the state of Texas, but if it's in Colorado or New Mexico, we do a snow accounting model up there to take that into account.
Okay. Question from Steve Fitzgerald. They ask, do you have a backup method to forecast peak elevation and time frame for urban watershed with heavy rainfall not forecasted that would peak within 30 minutes or less?
For us, we have a ton of books that actually left by Steve Fitzgerald that we could reference for, either measuring current water levels. You could look at analog events. You could look at rating curves, which would be the primary backup method. So you could say, okay, based on this stage and maybe this volume of water, what do we expect the water level to be? I found that through experience, using a prior event, looking at the rainfall distribution, looking at the volume, looking at the rate of rise, you're able to come up with a rough estimate of how high you think it's going to get, because you start seeing patterns. Engineered systems tend to act similarly because that's how they're designed. And so you're able to draw from past experiences.
In our case, if our model failed and we had to do that, we would kick back over to our National Water Center, who runs the National Water Model every hour, but there's a huge delay in it. So we would do that, or we have the ability to generate our own site-specific models, which are smaller scale, and we would then, if we observe the rainfall, we would put that in as an observed rain and rerun it, but it would only be for some of the smaller scale, I don't want to call them urban, just the smaller basins in our area. We would not have that capability of full forecast services across our entire 400,000 square miles. But we do have a couple, I want to knock on wood and say that our CHIPS model has been stable this entire time and has not failed us. And as soon as we would see the observed radar or the observed rainfall, we could manually input that in and then run our model based on that.
Okay. We have another question from Jason Pinza for Justin. How often should you recalibrate your models? And are there any instances where you needed to remodel rather than just recalibrate?
So for us, our models are fairly new. You could certainly in Harris County justify recalibrating every couple of years, because every couple of years, or throughout the year, we're adding new major watershed elements, detention basins or regional flood mitigation basins, channel improvements. But at some point, there's a break in that time where not as much changes. A big factor when it comes to runoff volume is, urbanization. We do have clay soils, and so clays really act like impervious cover, and so you do have some change there. And so we're actually in the process of slowly stepping through and updating our models kind of one at a time. But at one point, they have to be good enough for what you're trying to achieve at that time. But like I said, if they add some big watershed element, then that's obviously going to influence your forecast, and it's something that has to be included.
Okay. Question for Greg from Ranjan Matia. They ask, what's the smallest spatial resolution of the QPFs?
For our operational purposes, we break it down to the same 4-kilometer HRAP grid that we use for our observed precipitation. So we have a upscaling, downscaling methodology, so that when we get the data in, it is at the same 4-kilometer grid scale as our observed.
Okay. I'll give it another just a little bit longer to see if we have any more questions come in, but that's it so far. Well, thank you guys again. Thank you, Greg, and thank you, Justin, for those great presentations. And I think that wraps it up for our webinar.
All right, thanks for having us.
Thank you very much.
Absolutely. All right, bye, everybody.